The very final organic reaction is polymerization, or making a polymer. Polymers are incredibly useful materials. We use them to make all kinds of things. Sometimes we refer to them as being plastic. This is polyethyl terephthalate. This is bad quality astroturf. Polyethylene. Diaper? Polymethyl methacrylate. It's very good at absorbing water. Thank goodness. Polystyrene. Silk. It's natural polymer. Polybutadiene. It's an elastomer. More about that later. And guess what this is? How'd you know it was wool? Polymers are a huge part of our lives. Without them, the life we live wouldn't even be possible, because most things we use are made out of polymers. Natural polymers including cotton, DNA. That's right, we're made of polymers. Natural rubber, starch, cellulose, chitin, silk, and even keratin, the stuff that makes up our fingernails and our hair. It's the same stuff. Even proteins. Synthetic polymers include polyvinyl chloride, which we know as PVC or vinyl, polytetrafluoroethene, which we know as Teflon, polypropylene, polystyrene, polyethylene. There's a lot of different polymers, a huge number of different polymers, and each one has their own specific application. To name a polymer, what you do is you take the name of the molecule you made the polymer out of and you stick a poly in front of it, which means polyvinyl chloride was made with vinyl chloride. Polytetrafluoroethene was made out of tetrafluoroethene. Polypropylene was made out of propylene. So all you do is take the molecule you made the polymer from and stick poly in the front, because poly means a lot. If your molecule was wanna-cracker, it's poly-wanna-cracker. So polymerization links many small molecules, which we call monomers, into a much larger molecule that we call a polymer. It works kind of like this. We've got some monomer here. To the untrained eye, they would just appear to be paper clips. We're going to put this monomer into a polymer factory. Now, polymers do not form unless you add a catalyst to it. So we're going to use a catalyst, put the catalyst in here, and we're going to put the cover on, and we're going to give it a good shake, 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 shake. And then, after we've given it plenty of activation energy, we're going to pull out our polymer. That is a polymer. It's one large molecule made from many small molecules. These are molecules of chloroethene. F for 2 carbons, ene for the double bond, chloro because there's a chloro on it. So these are all chloroethene monomers. If we hit them with a catalyst, what the catalyst will do is break the double bond. And then, having nothing else to bond onto, because we're not reacting it with any other element, the monomers bond to each other. They join together to form a polymer. If you want to stop the growth of the polymer, you inject hydrogen into it, and the hydrogens will cap the ends. This is called polyvinyl chloride. It's used in making shower curtains, steering wheels, vinyl siding, even record albums. Another way we could draw it, because this is just too much to draw. Let's say we had 5 of these vinyl chloride monomers. Well, the double bond broke, and they joined together to make a chain 5 long. Therefore, the name of this polymer is polyvinyl chloride. This is how we can draw. It's a chain of these that's 5 long. If I had 5,000, the chain would be 5,000 long. Tetrafluoroethene, ethene, tetrafluoroethene. If I take n number of these, n standing for any amount from 2 to 1,000,000 or even higher, and I break them up, this double bond is going to break. And we're still going to have the fluoros there. And the chain will be n number long. So if I had 500 of these, the chain is 500 long. This is used for making non-stick coating in non-stick pans. How do they get the non-stick coating to stick onto the pans? That's a mystery I'll let you Google. Styrene, which is also known as phenylethene. A phenyl group is a benzene ring attached to ethene, phenyl, ethene. We take N of these, we break the double bond, and we make a chain N number long. Depending on the manufacturing process, this can be used to make either polystyrene plastic or it can be used to make styrofoam. Those two polymers were made from addition reactions. We broke a double bond. That's an addition reaction. But we can also form a polymer by removing H from one and OH from another and joining the two monomers together. Removing OH from one and H from the other and joining the two monomers. This makes an ester. A polymer made from esters is called polyester. Oh yeah. Stretch! Elastomers include such things as polyisoprene, polyisobutadiene, neoprene. It's used to make things like rubber bands, tires, sports equipment, inner tubes. Hey, belts, gaskets, and balloons. When these are made, though, the strands of polymer are not very strong. In other words, when this stuff was first made, if I pulled on it, it would be like pulling on taffy. It would just go bleh, and it wouldn't be all stretchy. So they don't hold up to wear, and they're a bit sticky too. So when rubber first forms, it's kind of like So to strengthen the rubber, the molecules are cross-linked with sulfur. Why? Sulfur forms two bonds. So one bond can be to one molecule, the other bond can be to the other molecule. And, much as this frog, holding these two twigs together, if we pulled the twigs apart, the frog would just simply stretch. Probably wouldn't be very happy about it. This process was discovered by accident by a guy named Charles Goodyear, who went broke a couple of times actually trying to develop this process. We use it to make rubber tires nowadays, toughen up rubber so it can stand up to a lot of wear, and it's bouncy and stretchy. At the molecular level, these molecules are all crimped up like this. When we put sulfur in between them, when we stretch them, the sulfur will give them a reason to come back and regain their original shape. This process of cross-linking these polymer molecules with sulfur is known as vulcanization. Thank you for joining us for this series. I hope you've gotten a lot out of it.